Okay, so we are going to look at some further applications. Again, we're still on the review part here, so we're gonna do further applications with Desmos today. Um, and we are going to look into ways to represent the functions that we discussed last time, and I just put them on the whiteboard, but we never really had a chance to represent them in Desmos and to see how easy it is to actually get them in Desmos. All right, so I'm going to share the following screen with you, and that's taking us to Desmos. And since I failed twice to actually show you where the app for Desmos is, it's kind of hidden here. It's kind of not so easy to find, but I found it finally, and I made notes yesterday after I found it. So if you go down, scroll down at the bottom of the page, there's a tab called Accessibility. If you click on that, that's going to take you here, and there's on the left side there's a link here for mobile apps. And these mobile apps, you will see that it has for both Android and iOS and iPhones. I'm going to click on the one for Androids, and there we go. So that's how you would install that. I'm pretty sure you will find that. So you find that in your Google Play if you have an Android. If you have an iOS, an iPhone, there's on the, I think that's in the App Store. So I think it's in the App Store on, excuse me, on the iPhone. You can also download this on an iPad if you have an iPad. All right. So that being said, I'm gonna just go back to the graphing calculator, and we're gonna do a little bit of experimenting here before we move on to something else. And that will be the following. So let's say here we want to represent constant functions. What did we say those look like? Well, they look like something like y equals 3. Or you could say f of x, oops, equals 3. And that's going to give you this horizontal line, which we discussed about yesterday. That was our first example. All right. Now, if you set f of x equals to something else, like yesterday we said equals 3 plus 2x or something like that, that's going to give you the blue line, which as we expect, goes through the point 3 on the y-axis. That's the y-intercept. We could write it the other way around, and maybe it's better that way. 2x plus 3. So everybody understands that the slope of this line is 2. Look here for the slope. Look at these points. So if you go 1 unit to the right, then the slope, the rise goes up by 2 units. So the slope is 2 for that line. I can represent a point there, 2 points on the line. So let's represent this one, 0, 3. That's going to be the y-intercept. And let's represent another one. So that will be 1 and 5 because it goes up by 2, right? So you will see how, over here. So it's 1 is here, right? So if 1 is here, yep. So it goes up. Okay, so let me zoom out. There we go. So zoom out here to see it easily. So if you go 1 unit this way to the right, then you go 2 units up. So that's the slope of 2. All right, so that represents the idea of slope and such. I'm gonna erase these things from the picture. So that's just by clicking here on the left side, clicking these buttons and then make them invisible. And I'm gonna represent another function, and that will be f of x equals x squared, for example, and that's going to be your usual parabola. There's a parabola right here. All right, so this parabola, we will do some other things today with a parabola. We will learn about transformations. Again, it's something that we learned in pre-algebra not pre-algebra, college algebra, pre-calculus and stuff like that. So we learned about those transformations. We'll review them today just in case, they're kind of useful here because they're examples of compositions, and we need to use compositions for the purposes of working later with a chain rule and things like that. So some things of calculus that use compositions intensively. All right, so that's the x squared, and then you can, I'm going to erase that, and I'm going to say another example that we did yesterday was this one, x cubed, and you can see that x cubed, now let's zoom out a little bit here. So x cubed is that shape that I promised you. It goes, even though it doesn't look like, this is going to go infinitely far to the right. So as you make it bigger and bigger and bigger, you will see that it goes over here far to the right, and actually for every point here there is on the right there is one on this graph that's above that point. It's the cube, but because this function grows really fast, we won't be able to represent it here on this screen unless I do it very small. And even so, the cube is a very large number. So even for 10, the cube is 1,000. So that would be really high up there on the graph. So so that's it's a little harder to see. It's not necessarily something that we will use very often, just in case, to just have an example of a function there that's other than the linear functions and the quadratic functions, which we are going to use very often. All right, so this is x cubed. And finally, we gave some examples here yesterday. I call all my functions f, as you can see here. So yes, any questions, folks? All right, so yeah, it's either some, I think someone's trying to tell me something. So all right, well, you have your mic open, so oops. Okay. All right. So so folks, for the other functions, so I was saying that I'm calling all my functions here f, but you can certainly call them some other letters. I can call functions like h or something like that. So I'm going to do here h of x, for instance, equals something else, or something like a square root. Now, the symbol for square root, you can find it here on this small keypad, and somewhere there's a square root. There we go. So the square root of x, and it's going to give you this graph here that's bluish here, and it looks like half of a parabola, which it is. It's half of a parabola, but it's like horizontally. And finally, so besides that, we said yesterday that we would also occasionally see examples like the hyperbola. So let's say g of x equals 1 over x. This hyperbola is very nice. Actually, I wrote a research paper on the hyperbola. It has some very nice properties. So oops, let's turn off the blue one. So it's the green curve here, which, as you can see, is very close to the x and y axis. And otherwise, it's kind of like a bunch of open arms in the x and y directions, and also the similar part on this other side of the plane. All right, so that's that, and finally the last example that we did yesterday, and I didn't have time to graph that, but it's very easy to graph. Let's say you want I don't know, FGH j of x, another function. And that will be sine x, for example. So I'll say sine x here, and we'll represent the function sine. And we are going to discuss a little more. So, so the only reason why I'm doing this, the comprehensive thing is to trying to familiarize yourself, everybody with Desmos, because we're going to use it, to kind of represent everything that we do here. We represent graphically. And also there's one trick here. So so one thing I want to insist on. Remember what I said yesterday, that in calculus, all the trigonometric functions, all the angles should be measured in radians, because the calculus that we learn here works for degrees as well if you measure angles in degrees, but the formulas that we learn here are only formulas true for radians. So you will see that the limits and the derivatives and such will be true only for radians. We use specifically some properties of measuring the arcs on a circle. And in particular, when you represent the function, a function like sine x or cosine x or so, what you want to do, you see it says here, if you click on this point, let's click on this point here, it says 2 pi 0. But on the grid, it's not obvious that this would be 2 pi here. We know that that should be 2 pi. So what we do here, we go on this, somewhere on this right side, there's a symbol here called graph settings. It's kind of looks like a wrench, and you click on that, and that's going to give you the possibility to put your axis in radians. So I'll do the first one here, the x-axis. I'll check that to radians. So I'll say here radians, and I want to do, I don't have to change anything here, just the step. I'll say a step of pi. I'll just type set P and I, and that's going to make the symbol pi, and that's going to give me everything I need. And you can just click away from that, and it's going to put the 2 pi's on the x-axis. So again, the trick, folks, was to go here where the wrench symbol is and to just put the step of pi for the x-axis. You don't have to do that for the y-axis because that we still need to measure numbers there. So remember that sine and cosine are just some proportions. For instance, sine is the ratio, which is a ratio of the opposite over hypotenuse if you have a triangle with a right angle. So it's a quotient of 2 lengths. So that's going to be just a number, a ratio, right? All right. So that makes the graph of sine and puts multiples of pi. So this point here is pi 0 on the x-axis, 2 pi, and so on. All right, so that way you see sine. Remember that we said yesterday sine goes through 0, 0. And to finally finish up this review from yesterday and the graphing part and such, I am going to do another function, and that's going to be cosine x. All right, so we'll do cosine x, and let's turn off sine because it's confusing. Where is sine? Here. All right, this is cosine. As I told you, cosine is like a bell shape from negative pi over 2 to pi over 2. So it starts here at the top. It starts at the point 0, 1, and goes down and up and down and up and down and up. Also a wave like the sine function, but it's slightly displaced. In fact, if you compare the two of them, notice how the graph of cosine, if you push it to the right by pi over 2 units, it's going to overlap the graph of sine. But again, that's not so important. So just remember that we're talking about some wave functions. Finally, what I need here is one more function, and I'll be done. I'll call that t of x, and that's going to be tangent of x. And look at tangent, look at that. That's so beautiful picture here. It's a bunch of graphs that I told you they look like the x cubed function, but these guys they never they never leave like these branches of tangent. So let's say here I want to draw just a part of it. So I'm going to perform the trick that I used yesterday for piecewise defined function. I want to define this piecewise. And I want to say, I want this function to be defined only from negative pi over 2 to pi over 2. All right, so I'll say negative pi over 2 strictly less than x, strictly less than pi over 2. Remember the number pi, you simply typeset the letters p and I, and it's going to turn into a pi. And then you say here, colon, and the formula that you want is tangent of x. So I want tangent represented only on that small interval. And look at that. So we get this graph over here, only that particular branch. So remember, negative pi over 2 would be the point over here. What is that? Here. It doesn't show on the graph. So let's represent that on the graph. So the point negative pi over 2, comma, 0 will be represented on the graph right there. So see, this one here is negative pi over 2. Pi over 2 will be the symmetric on the other side of the graph. All right, so now my question for you folks, does anybody remember what the problem is, why we don't want to represent the tangent function at, there's pi over 2 and 0, let's put that there as well. Does anybody know why we don't represent the tangent function? We don't talk about tangent of pi over 2. Do you remember what the problem is? So you can say in the text, folks. You can in the chat there if you know the answer. So why is it that yeah? So somebody already answered. There we go. Undefined slope. That's true, but remember, yeah, that's true. So the slope is undefined. But why is it undefined, folks? So what is the problem there? So indeed, if I say tangent of pi over 2, it's going to tell me it's undefined. Look here. So if I say tangent of pi over 2, it's undefined. See, it tells me here. That's true. But why is it undefined? What's the thing behind that? Look at the definition of tangent. So what happens with tangent? Tangent of pi over 2, folks, is the same as sine of pi over 2. Oops, sine of pi over 2. Okay, what did I do there? All right, let me get out of it. Divided by what? By cosine, right? Do you remember that? All right, so here's what happens. Oops. Can you explain me based on this expression here, what exactly is the problem here? Why does that not work? Does anybody remember why that doesn't work? That's correct. There we go. Yeah, we cannot divide by 0, folks. Yeah, cosine of pi over 2 is 0. Indeed. Yeah, we cannot divide by 0. Very good, folks. So we got a couple of responses here. That's true. So that's true, folks. The denominator here, cosine of pi over 2, is 0. And in math, you all know that we cannot divide by 0 because that's highly illegal. The cosine of pi over 2 is 0, folks. Yeah, so that is the main reason. That is the reason why tangent is not defined in pi over 2, and we don't want to talk about that. All right, so this quick review, I'm hoping that brought back some memories of trigonometry. So again, we are going to review various other things about trigonometry next in the future lessons, not next necessarily. But yeah, you want to look at, you want to brush up on your trig functions, you know, just basic values. So things like the ones you can see here, no things like sine of pi over 2, cosine of pi over 2, sine of 0, cosine of 0, things like that. This is what's going to be mostly used in calculus. We don't need a lot of trigonometry. In fact, there's good news if you didn't learn a lot of trigonometry. The good news is that you won't need a lot of that here in calculus. Just some basic formulas like cosine squared plus sine squared equals 1 and things like that. The formula for tangent in terms of sine and cosine and such. So the main bulk of trigonometry is actually useful for calculus 2. So those of you who do calculus 2 will have to do a serious review of trigonometry. Who will take, so if you take calculus 2. However, if you only take calc 1, you don't need much of that at all. So really very basic things of trigonometry, which can be reviewed quickly when we discuss about those things. So I'm not gonna insist any further, and I am going to move to the new subject, which would be new functions from old functions. If there are any questions, do let me know, folks. So I can address those now before I move on to the new lesson. All right, so it seems like no questions. I'm going to stop sharing this screen. We will go back to these kind of functions. All right, folks, so let's, by the way, these recordings are on YouTube, so in case you miss any details here, so you can always go there. Folks, I am going to share with you another screen. Come on, show up here. All right, I'm going to share with you the whiteboard, and we're going to write on the whiteboard for a little bit here. So first of all, the new lesson here is 1.3. This is also a review lesson. And it says new functions from old functions. From old functions. All right, so this is the title of the lesson. Again, you don't have to remember much of that. So what's going on here? What do we discuss here, folks? The things that we discuss here is basically various aspects of what we called in pre-calculus or the college algebra or so, compositions of functions. So various aspects of compositions. And one aspect of compositions is going to be given in the following example. So pay attention here the next couple of minutes, and you will know everything you need to know about this lesson, because really it isn't that difficult. So let's take a formula, something like f of x equals x squared, right? And we know that that's represented, if we represent this on a graph, and I did this many times already in this class, and I'm going to do it again, it's a parabola like that. And in calculus, we want to discuss functions that are a little more complex. Something like, let's say, g of x equals negative x squared. So what is the difference between the two of them? Well, the difference is minor. It's really just that sign there, which however, is very important, because once we throw in a minus sign here, can anybody remember what happens? So I don't have Desmos open with here, but if I were to have Desmos open, what happens with a graph of x squared if I throw in a minus sign? Yes, so let's see. There's a couple of answers already. 3 answers. It's open. It opens down. Yeah, it's flipped. That's correct. It's reflected over the x-axis. It's flipped upside down. So indeed, yes, it is. It does open down. Very good. So this is a very basic example of a composition. So what is the composition here? So the composition is the following. So the structure of this problem here is as follows. So we have a function h of x equals to negative x, and then we have the function f of x equals to x squared. And what I do, I replace negative x from the formula here by this guy, by x squared. So I replace x by the second function, and that is the result is negative f of x or negative x squared. So this is an example of a composition of two functions. So what I get here is really what's called in college algebra or in pre-calculus H composite with F with a small circle like that. This is an example of such things. So you can see that by compositions, graphs are kind of changing, and they're changing in significant ways. Even though the shape doesn't necessarily change a lot, it does change, however, the orientation, and that's very important. All right, so another example of a composition is the following. All right, so again, I start with the same story with f of x equals x squared, but I'm going to twist it in a different way. So I'm going to say right now, g of x, I'm going to do x plus 2 squared. Now, remember that x squared was this one, was that's y equals x squared. What do you think will happen to x plus 2 squared if I had Desmos open and if I were to represent this one here? How does that change? Where does the graph move? How does it move? Does anybody remember? Take a guess, folks. This is not necessarily an easy question. So yeah, so somebody says, let's see, is Nathan, horizontal shift to the left by 2 units. Excellent job, Nathan. Very good. So indeed, the graph moves horizontally to the left by 2 units. So so it's going to come over here. So yeah, this is what we're going to get. So oops, doesn't look very pretty. So you get the idea, folks. I apologize on the tablet is not so easy to make pretty pictures. All right, so you get the idea. Let's delete it. There we go. All right, so there we go. So this point here is -2. Now, how do we figure out easily that that point would be -2, the vertex? So that's a vertex of a parabola. How do we know that that's -2, folks? We know that that's -2. It's the point where this equation becomes 0. So remember this parabola, the formula becomes 0 where it touches the horizontal, the x-axis. And it touches the x-axis, so it becomes 0 when x plus 2 is 0 or when x is -2. So that's how you figure out. So x plus 2 equal to 0 implies x equals -2. And this is where the vertex of a parabola will be. All right. So these two are examples of new functions obtained from the old ones. Now, this is clearly another example of a composition. So what is the formula here? The formula here is slightly different now. So the formula, let's take the formula h of x equals x plus 2. And we had the formula initially, initially we had the formula f, one second, oops. Can't get out of the eraser here. So initially we had the formula f of x equal to x squared. And what you see here, folks, what happens, we take this guy here and we plug in the formula of f. So we substitute x by x plus 2. And this is the composition that goes like this. F circle h, I'm sorry, not g. F circle h. So in other words, this is f of x plus 2, and that is the quantity x plus 2 squared, because that's what f does. The formula for f takes a quantity and he squares that. So that's how we get another example of a composition. And again, you see that the graph becomes very different from the initial one. All right, folks. So this is pretty much the idea of this lesson, to do a bunch of transformations to various graphs. There's examples in the book. The most interesting are those that happen to the sine and cosine functions, but we will rarely use those. It's most likely that you're going to use them in physics, if at all, not necessarily in math. So, so what happens in physics, and I'm going to give you another example here. So this would be our third example today. Let's take a slightly more complex function. So this is the function. Let's say, which one should we take? So let's take sine x. It's the easiest. It goes through through 0, so you don't have to worry much about anchoring the function itself. And I can do the following things to this function. First of all, I can do the first thing that I did to the x squared function. I can throw in a minus sign here, but instead of a minus sign, because that's not so interesting if I throw in a minus sign, I could say, let's take this function g of x equals 3 sine x. Now, if I were to represent the graph of this second one here, this number 3 here, it's called amplitude. Why do you think that's called amplitude? What do you think happens with the graph of sine? Can anybody tell me? So amplitude is the number 3 here. So what do you think happens? Let's see. The waves get taller. That's true, folks. That's true. Very good. Very good, Garrett. The waves get taller, actually 3 times as tall as the initial ones. So let's actually, since I'm I'm probably going to be able to do a graph, but I'm not going to be able to do a nice one here. let's actually represent that in decimals and let's convince ourselves that that's the case. So I'm going to stop this share and I'm going to do a new one. All right, so everybody should be able to see decimals. Let's clean up this stuff here. What's going on? All right, sorry about that, folks. Let me clean up the stuff that I wrote earlier. We wrote a lot of stuff. All right, so come on. All right, so let's do, first of all, let's do y equals or f of x or whatever. So f of x equals sine of x. All right, and let's do a, let's zoom in a little bit here. So you can see this is the sine function. And look at these folks. So, so what I'm going to say, g of x, oops, or then we could call f of x, but now let's call it a different letter. So equals 3 sine x. All right, so I did 3 sine x. Look at that. Look at what happens with waves. The waves get 3 times as tall as the initial one. So they still go through these points. So the frequency doesn't change. It's just the amplitude, the size of the waves changes. So it becomes 3 times as big as the initial one. All right, so so that is what happens with the waves. All right, now what do you think happens? So I'm gonna share the whiteboard again with you. What do you think happens when we change this function differently? So when we do, let's say sine of 2x. Now this number 2 here, so so I told you that number 3 here, just a review from pre-calculus or trigonometry, is called amplitude. The number 2 here has to do with angular velocity. So what this tells me here is that I still go on the graph of sine, but I go angular velocity. It's not exactly the angular velocity. I have to be a little more careful here. I should say it has to do with angular velocity. But the idea here is that I'm going on the graph of sine twice as fast. Or I'm going on the unit circle. Remember that sine measures the y coordinate on the unit circle, but I'm going twice as fast. So, so of course, if you go at a faster speed, you are going to reach the target destination. So if your target destination was to, so remember we measure with sine again. We measure. All right. So if this is the angle, this is the angle theta. Sine theta, folks, so I'm on the unit circle here. Sine theta measures how your displacement, this is sine theta, this segment, your displacement in the y direction. So, so what I'm talking about here, if I go at twice the speed, the idea is that I'm going to reach the top of a circle here, the furthest point from the origin. I'm going to reach it in half the time that I used to reach it before. So if I go at twice the speed, I'm going to go around the circle twice as x goes in the, as x is in the interval 0 to pi. So what's going to happen with this graph, I'm going to see the exact same pattern, but I'm going to see 2 repetitions of that pattern, of a sine pattern, you know, going up and down in a wave. I'm going to see 2 repetitions of that pattern in the interval 0 to pi. Let me convince you that that's the case. All right, so I'm gonna clean up this stuff here, and I'm gonna say f of x or g of x or whatever, some other letter, equals sine of 2x. And look at that, 2 times the pattern. So you see, if you look carefully here, what happens is I'm going once, and I got the pattern down, and then I'm going one more time, and once I reach 2 pi, the initial pattern was going up, going down, and coming back to the horizontal position. Well, this happens twice, in that same interval length. So because I'm going twice the speed. So that's why that number 2 has to do with the angular velocity. It's not exactly called the angular velocity. You have to be a little careful there, but that's the main idea. So that's something that you will use in physics. All right, we will discuss about that when we calculate derivatives. We'll discuss about that a little more. All right, folks. And now let me point out. The main thing that I was getting to in this lesson with these examples is the idea of composition. So again, the composition of two functions. This is again a review topic. F and G is denoted like this, is F circle G, and it really is a function whose values are calculated by replacing x in the formula of F by the function G of x. So examples of compositions are numerous out there in practice, and this is something that everybody needs to be familiar with because we're going to apply this when we discuss the chain rule, for example. So let's do other examples of composition. So let's say f of x equals square root of x and g of x equals x squared minus 1. What is the compositions of this one? Well, f circle g will be, as we said, we replace x from the formula of f by the formula of g. So we'll take g and we'll put in here, and that's going to give us the square root of x squared minus 1. Does that look good, folks? All right, now let's do the composition the other way around. So let's do G circle F. Now I'm going to leave this as a small exercise for you. Can somebody do this calculation and tell me what it is? So I intentionally did that this way so you can actually typeset your answer, because it's going to be easy to typeset your answer in the chat. So do that quickly and typeset the answer. I'm going to wait for somebody to typeset an answer in the chat, and then we'll go from there. That is correct. So yes, so a couple of folks already got that. So it is x minus 1. How do we get that? Well, simply just remember that this is the same as, so now we do it the other way around. So we'll replace x from here, from the formula of g, by square root of x. So this is going to be square root of x squared minus 1, and that is going to be x minus 1. So I intentionally made it easier so you can actually typeset in the chat. All right. So this is the composition, folks. Now, what we notice with this composition is that sometimes the composition of two complex functions turns out to be a simple function. However, this is not the way we're going to proceed. We're not going to take two complex functions, do a composition, and make them in an easy function. We're going to do things the other way around. So we're going to do complicated examples of, simple function. Composite with simple function is going to give us a complex function. And then we're going to discuss that function in terms of, looking at the terms of the composition. So we're going to discuss about limits, derivatives, and things like that. All right, folks. So this is pretty much the content of today's lesson. So it was a review, an essential review about compositions, and the applications were those in the graphs and such. Again, it's so this was the main problem, and we'll discuss more when we get to that. But the compositions were the main problem why calculus for a number of centuries didn't make much progress because people couldn't understand how to relate the graphs of two functions with the graph of the composition. So it's very difficult. That's why I'm not even going to attempt to make some sort of relation for these complicated functions. And then because of that, until they figured out the algebraic formalism, to actually deal with the problem they were dealing with, things like tangents and velocities and things like that, it took a number of centuries to actually figure that out. And what we learn here, folks, what we will learn in calculus is really something that is the result of a lot of a long time thought process. So it's not necessarily going to be something that you can pick up in a second or two out there, because a lot of people have put a lot of thinking into solving these problems that we learn about today. So in this calculus class here, please remember that there might be topics that may look a little more challenging, but don't despair, because we have them cooked for you properly so that you can actually digest them easily. However, don't think that don't feel bad if you find anything challenging, because again, what you learn here is the result of a lot of centuries of thinking and a lot of people thinking about these problems. So until the solutions to these problems were crystallized, it took a lot of time. So humanity has evolved a lot, and nowadays we find calculating limits and derivatives and things like that a very easy process. But it wasn't considered easy, let's say 100 or, well, maybe 100 years ago it was, but 200 years ago or so. So this is what we will get into. We will get into learning how to describe, essentially, how to describe various graphs of compositions. That's kind of what calculus boils down to. And once we learn how to do that, we will discuss about tangents and slopes to graphs and things like that. We will be able to solve very difficult problems of maximum and minimum, etc. So that's kind of where the calculus class goes. I have one more section to cover about this review, and that's going to be done Friday. And we will essentially be done with this review. And after that, we will delve right into the abstract calculus notions. But until then, I am going to close the class here, folks. If you have any questions, do let me know. So I'm going to stop the recording. I don't have anything of importance to announce at this point in time.